To all of you, welcome to the second day of the conference, and we'll have the first plenary and only plenary lecture of today. So it is my privilege to introduce Professor Tom Hughes, holder of the Computational and Applied Mathematics Chair at the Oden Institute at the University of Texas at Austin. He is a globally recognized pioneer in computational mechanics. He has developed foundational advances in finite element methods, from streamlined upwinding Petrov-Galerkin stabilization to variational multiscale and isometric analysis. And his framework really underpins, I would say, most of the commercial softwares that are currently available. He has been the founding president of UACM and IACM. He has been recognized with so many awards that the list never ends, but I'll mention a few of them, like the Timoshenko Medal, Von Karman Medal, ASME Medal, and election to the US National Academy and Royal Society, and all of them really just recognize his outstanding contributions to the field of computational mechanics. It is my pleasure to welcome you at Porto.
Thank you very much for that kind introduction, and thank you for inviting me. You too. All right, so I'm going to be talking about variational multiscale methods, and sort of the theme of the talk will be the two roles that they play. One, of course, I think most people are familiar with these techniques to develop stable and accurate numerical procedures, but they also provide a framework for building models, so-called models. Sometimes we don't solve exact equations. We solve some kind of a model, like a turbulence model, for example. So this is a machine that can guide you in how to build those things as well. So with that, let me just give you a brief outline. This is a little bit of a history talk, because I will start from the beginning. And the beginning is stabilized methods, which were around for about 15 years or more, until I finally figured out where they came from, and they came from the variational multiscale framework. So I'll go through a bit of a tutorial on stabilized methods, assuming that not everybody is familiar with these things. And some of the topics that you see there will be model problem, then SUPG, Galerkin least squares, space-time formulations, which have some nice properties, and the system concept when you're dealing with systems of equations. As, for example, if you were dealing with compressible flows, a system, you have 5 equations and 3 dimensions. And some of the issues. So I think the theme in that will be there's sort of a paradigm that is simple and applies to a lot of things. And it's kind of subsumed by the variational multiscale method. And I was going to do that for compressible flows, but I decided it was maybe a little bit clearer to do it for incompressible flows. You'll see the idea, because the nonlinearities are simpler and explicit, and you can sort of trace them and see how the method evolves. And in that context, you're actually, in a sense, not building so much of a numerical method, but you're building a model. Okay. And I'll compare then what you get with just using a stabilized method approach. You get more. Nonlinearities will spit out more. And then I will use this sort of concept of using it as a modeling technique to investigate the Boltzmann equation. The work on the Boltzmann equation is initial work. Okay, so with that, let's go. Not in that direction, this one. All right, so if you wanted to get started with stabilized methods, these are sort of, I think, 4 landmark papers. The first one is when we finally started to understand what was wrong with artificial diffusion methods, classical upwinding methods, and that was published in a ASME book in 1979. There are a whole bunch of conference papers. In the early days of finite elements, lots of the papers were just conference papers. We didn't even publish them in journals. And as a result, the first paper that subsumed all of those conference papers was the 1982 paper here by Alec Brooks and myself, my former student. And that one tends to be the one that people point to because it was sort of it's a large paper. It was 60 pages, as you can see. And then that concept that was originally introduced to deal with convection operators that were different from what you normally utilize in solid mechanics, say, where everything's elliptic. That concept was shown to be a rather general concept, and it also solved this problem of pressure and velocity or displacement instabilities in a different way. You could avoid the requirements of the Babushka-Bretzi condition. And then finally, this was sort of blown up into systems when we were working on compressible flows in that last paper. The Galerkin squared method for systems was presented. So that would be a starting point for learning about these things. So let me give you an example. And I hope this is simple enough that everyone can follow it. So consider the scalar steady advection diffusion equation. So here you have diffusion, basically just a Laplace operator, and here you have advection. Okay, A is a given velocity here that we'll assume for simplicity is divergence free. Kappa is positive. Okay, so we will not get into boundary conditions. Boundary conditions are always a problem no matter what you do. When I wrote my company wrote a compressible flow code in the 1990s, the modules for the boundary conditions were enormous. We had 80 different sets of boundary conditions for for compressible flows. And the solver was like this big, and the boundary conditions were that big. So that's why they call them boundary value problems. They really are a problem. Anyway, so what is the key parameter here? The key non-dimensional parameter is the Peclet number. It represents the competition between the advective scale, the magnitude of the velocity, and the diffusive scale, the conductivity coefficient, on the dimensions of the mesh. So you can render the equations non-dimensional by exploiting the Peclet number. And when you do numerics, there is a similar concept, the element Peclet number, which is based on the mesh scale. And for, let me see if I can get on the mesh scale here, you can see here, this is the element Peclet number. We just normalize it by 2 for aesthetic reasons. So we're interested in the entire range, 0 to infinity, for that parameter. We'd like to have methods that are uniformly accurate and stable, no matter what the Peclet number is. Now, the case of, let's say, A being small or 0 is just the diffusion operator. It's a symmetric linear elliptic operator. It's trivial. And any Galerkin finite element method would just eat that up. On the other hand, when this guy gets big, that becomes problematic for classical technology. So that's viewed as the numerically difficult case. So here's an illustration of what you can see in an equation like this. It's perhaps the simplest model of a boundary layer. So this is just in one dimension. This should be an X, not a Y. I just noticed that. And what you have is, if A is 0, you just get the simple solution between the boundary conditions of 0 and 1, a straight line. And then as A is increased, the solution becomes exponential. And as the Peclet number increases a lot, it can create a very, very thin boundary layer. So no matter what your mesh is, you can always pick a Peclet number such that the boundary layer lives inside the first element. So it's a subgrid scale, if you want to think of it that way. So let's begin where we usually begin with finite element methods, with a Galerkin method. So just take a typical finite element space, and we look for a solution in that space such that for all weighting functions in the same space, we have this variational equation, a bilinear form, a linear form. And you'll note that the bilinear form is in the integration by parts format. This gives you conservation as you get into more complex situations. Not only does it give you conservation, it gives you conservation under arbitrary quadrature. You can be using a very inaccurate quadrature, and you'll still get conservation if you are in the integrated by parts format. So the remark is that the Galerkin method has very bad stability properties when the Peclet number gets large, just larger than 1, which is not very big, in fact. And you get spurious oscillations. So this cartoon kind of represents what happens. So if alpha is big, you get this thin boundary layer. Say this is your mesh where the green points are just representing nodes, and you'll get a solution just like this. In one dimension, it looks bad, like this. You do it in multi-dimensions, it becomes complete chaos for problems like this. Whenever you have a downwind essential boundary condition, as you do here, you get chaos. So the classical technology for fixing it was artificial diffusion. You just pump in some, let's say, mesh-dependent diffusion, make this big enough to damp out all those oscillations. That's an overkill technology. It will mess things up in different ways. It will stabilize things. You will destroy accuracy, and you'll actually get some non-physical phenomena like crosswind diffusion. Now, the features of the stabilized methods are illustrated here. They're similar. You start with the Galerkin method, okay? And then what you add in is something that is proportional to the residual. The residual is the measure of the lack of satisfaction of your discrete solution when you substitute it into the equation. LU equals F is the equation. L is the entire advection diffusion operator. So that's the residual. And it is weighted by, in this case, in SUPG, by the advection operator on the weighting function, and here by the entire operator. Now, those look different, but essentially, when you define this in an appropriate way to get optimal convergence rates, this parameter tau, these things behave essentially the same. So the important thing here is these are residual methods. The Galerkin method is a residual method. If you put the exact solution into the Galerkin method, it satisfies it. If you put the exact solution into these stabilized methods, the equation is satisfied. On the other hand, it's not satisfied if you put it in here. You have modified the equation you're solving. Okay. So these are integrals over element interiors. Don't worry about higher order continuity or things like that. You don't need it. These are just integrals over element interiors. Okay, so the artificial diffusivity in the typical method is order h. The parameter tau, I'll say more about it in a moment, it's order h over a for alpha large, and order h squared over kappa for alpha small. And this reflects the fact that this equation really needs different treatment in different regimes. Now you want to do that continuously so you have uniform accuracy, and we'll see how to do that. Let me first say a little bit about the importance of the residual. This is the residual, RH, okay? Now this is the residual of the exact solution, it's 0. Subtract those. And what you see is that the residual is actually proportional to the error in your numerical solution. So when you are controlling the residual, you are reducing the error, okay? You are not hitting features of the solution that are real features, you're only hitting errors, okay? That's the difference between these methods and the artificial diffusion methods. Okay, so RH is an a posteriori measure of the error E. Now, you can do an analysis, various types of analyses that will all lead to the same conclusion. If you select the tau parameter according to this formula, where this is the element Peclet number, and the plot of this function, C tilde, looks like this, okay, you will get not only a good solution, you will get the exact solution. For any mesh, the mesh doesn't have to be uniform. You get the exact solution at every node with linear elements. Okay. So the unfortunate thing is these are called stabilized methods. It sounds like you're hitting it with a hammer to stabilize it. You're building an accuracy. And in more general circumstances, the properties of that parameter are identified, at least in my work, using functional analysis techniques to actually prove convergence theorems. And you can do it for extremely complicated situations. So you can design these things. So the additional terms, the stabilization terms, they improve the stability of Galerkin's method. Classical artificial diffusion method, as I said, is overkill. The accuracy is always limited to first order, independent of the polynomial order. So it's not a higher order accurate method. So the stabilized methods, they are residual methods. If you replace UH by U, as I said, the equations are satisfied, unlike the classical artificial diffusion methods. So it's an interesting combination of good stability and good accuracy. And you can prove mathematically that you get global error estimates for smooth solutions of order p plus a half. So it is a higher order accurate method. If you increase p, you get more accuracy. And it's usually p plus 1 in practice. These are the same types of estimates you get for discontinuous Galerkin methods. And these methods have a lot in common. Very often, practical discontinuous Galerkin methods in big codes actually use these stabilization techniques too, because you still need them inside the elements. Now the interesting thing is when you have rough solutions, you get the same rates of convergence outside of small neighborhoods of the layers. And these are called interior estimates or localization results. You can mathematically prove that. And these things are impossible for Galerkin. You get this propagation of error or global pollution. And well, you can take your pick what you like. Galerkin least squares is a bit simpler than SUPG from the analysis point of view, but from the implementation point of view, SUPG is a little simpler. So take your pick. So let me just show you a couple of test problems and indicate why they are challenges, classical challenges. So this is just using SUPG, advection-dominated flows, and we're using spline spaces, higher order spline spaces of order P. So this is a test of accuracy. This is the advection of a sine hill. So you have a square domain, as you can see. You have a rotating flow field. It varies linearly from the origin going outward. Very small diffusivity, so these are advection dominated. And what happens, you put on an internal slit, you set a sine hill. Now what should happen is the flow should carry that around, rotate it around, and because it's basically pure advection, it should come right back and be exactly the same. If you do this problem with a classical upwind method, by the time you come around, the hill is gone. It becomes a pancake. Okay? So this is a test of accuracy. These are quadratic elements, and these are sixth order elements. And basically the solution is exact in either case. These methods also solve this problem of spurious crosswind diffusion. And that's present in any isotropic artificial diffusion method. And you can see there's nothing spurious about these solutions. They're absolutely perfect. So a classical upwind method will destroy this. Now, this problem is more a problem of robustness. This is advection skewed to the mesh. You set a boundary condition of 1 here. The flow velocity is at angle theta, as you can see. Again, you're advection dominated, but you have hard zero boundary conditions on these outflow boundaries here. So in a very small layer, actually of order, the inverse of the Peckley number, you'll have a very, very thin layer in this outflow boundary here. And of order square root of the Peckley number, you have an internal layer that propagates. So they have different mathematical character. Okay, now, what is the mantra in finite elements? Low order ones are much more robust than higher order ones for difficult problems. Well, let's try this with 15th order polynomials with 14 continuous derivatives. You wouldn't think that's a normal thing to do. This is the solution. You see that the thinness of the boundary layer there? That's captured within one element. The solution is making a 90-degree turn there to pick up that boundary layer. Okay, also over here. Now, to get an idea how big the elements are, what I did is just interpolated this result with bilinear elements here. So this is not the solution. This is an interpolation of this onto a bilinear mesh. You can see how big the element is. Okay, You can see you're actually getting subgrid accuracy. That's sort of a feature of some of these methods. And this is just a 20 by 20 mesh, but the support of these functions is 3/4 of the mesh. Okay, so let's move on. The natural way to take these methods to time-dependent problems is via space-time finite elements. So rather than introduce some ODE solver, which makes proving theorems rather difficult, especially when the mesh is moving as a function of time, as they are here. So what we're doing here is we're going to take a slab, and we're going to just throw finite elements into the slab. We'll use the stabilization concept in the space directions, and we'll use discontinuous Galerkin in the time direction. So you take the idea, and again, you start with the Galerkin version of everything. You take the steady operator here from Galerkin. That's the bilinear form, the linear form here. And then you add the integrated by parts time derivative term with a term on the top of the slab. When you integrate by parts, again, this will cancel, and you'll get another term that hooks up with this one here that is bringing in the initial condition from the top of the previous slab. So that's the formulation of the initial value problem. And you get weak continuity enforced, and I'll say a little bit more about that in a moment. How do you stabilize it? Well, you do the same thing. Now you have a time-dependent operator. You have the time derivative in addition to the spatial part. That's your residual, and you can weight it in the sort of Galerkin least squared format with the entire operator. A very simple concept, the same concept. So the interesting thing about this, if you understand the mathematics of the formulation, the time-dependent problem is done in exactly the same way as the spatial problem. Again, you get higher order error estimates and localization results in terms of the order of the polynomial, the space-time polynomial. You don't even have to think about a time integrator. It's built into the formulation just by the finite elements in space and time. You achieve unconditional stability for any choice, and you just have to solve a linear algebraic system on each slab. So, simple example. Suppose you have one spatial direction, and time is slanted here, as you can see. So this is the thickness of the slab, say, is delta t. And you want linear finite elements in space. And then what you would do is you just extrude that in time. This would be constants in time. Constants in time are a legitimate interpolation. You basically get something that is sort of backward difference-like in the space-time formulation when you do that. If you want higher order accuracy, you can go to linears in time. So these elements in space-time are bilinear, so this is linear in space, and then you just take it down here for the basis function, and you have one over here. So you'd have like 2 points in the slab. Now the interesting thing is you get a superconvergent effect at the top of the slab. The integrals on the top, everything is conserved over the space-time volume, and you get a superconvergence on the sort of the outflow boundary, which is the top of the slab, outflow in the time sense. And when you use polynomials of order, say 0, 1, 2, 3, 4, for the time discretization, you get order of accuracy 2k plus 1. That's a big boost. So for a linear element in time, you get third order accuracy. Quadratics, you get fifth order, and so on. You might wonder, where are all the even guys there? If you enforce the continuity of the solution across the slab, you just started off with that, you get rid of one set of equations by doing that. When you do that, you'll get 2, 4, 6, and so on. So all the even convergence rates can be obtained too. And many people do that because they like to enforce continuity. What that means is you're using the same mesh in space from step to step. The way the math theory goes, the structure, the finite element discretization in one slab can be completely independent of the discretization in the next slab. You still get optimal error estimates. So people always worry about projection errors when they go, with techniques like this. Everything is built into the formulation. And you can go to systems. So a system would be something like a compressible flow system where you have 5 equations. You have mass, 3 momenta, and then you have energy. And so you have a vector of unknowns, say 5. And you might have a coefficient matrix on your time-dependent term. And you have the spatial operator, the system analog of advection and diffusion. Okay, so that's what a system looks like. Symmetric systems have very special mathematical properties. So a symmetrical system, all the coefficient matrices will be symmetric. And the one that's multiplying the time derivative term is positive definite. And the diffusion matrix is positive semi-definite. That's the case for the Navier-Stokes Fourier equations of compressible flow. They can be written as in system format like this as a quasi-linear system, where the coefficient matrices actually are functions of the solution. So again, how do you build a method? You start with Galerkin, integrated by parts. You add stabilization of the system, and now this tau is a matrix, okay? And typically it's not diagonal, only in very special cases will it be diagonal. Now, how do you design tau? Well, tau has been sort of the subject of continual research, how to make it better and better. And I think the most sophisticated techniques have been developed by Taifun Tezuya and his colleagues, Kenji Takezawa and others. And this book is a good place where it summarizes a lot of the results at the time of the book, and then more recent papers where they've refined these things quite a bit for different applications. So how do you develop now space-time formulations for the system? Well, you do the same thing you did in the scalar case. Start with the Galerkin part in space, integrate it over the time slab, and then add the integrated by parts form of the time derivative. And that gives you the weak continuity across the slabs. Now these, conceptually, these are linear methods. And you'll see later on from VMS, VMS is introducing how to really bring in the nonlinear effects in a consistent way. These are linear methods, and they're going to produce approximations to discontinuities like this. You might get an oscillation about the discontinuity, but it will not propagate. That's the interior estimates. You don't, in a neighborhood of the feature that's not resolved, those errors will not propagate. The problem with higher order accuracy and the desire to achieve monotonicity of profiles, these are incompatible. You can prove that. So no linear higher order accurate method will produce monotone profiles. So what to do? Well, very early on, we started to introduce nonlinear operators to control oscillations. And at first glance, it just looks like an artificial diffusivity, but you make the artificial diffusivity coefficient a function of the residual. So when you put the exact solution in again, these things vanish. So you can get more stability around these features, and at the same time, excuse me, at the same time, you can get higher order accuracy. And that's been proven also mathematically. So these techniques are in wide use. Boeing has SUPG codes. This is from Dassault Aviation, their SUPG code, which actually was written, at least the initial versions of it were written at Stanford by my graduate students who went on to populate the aerodynamics group at Dassault. So this is a calculation. This is a high lift configuration. It's a turbulent flow, and obviously 3D. They design everything on the airplane this way. Typically they do preliminary wind tunnel testing, then it's all computation right up to the very end, and then they verify that the computations are correct by doing wind tunnel testing. In the old days, they'd be doing wind tunnel testing all along. They do over 10,000 calculations like this every year, and this is a small company. I know, like the Boeing code, the Boeing wing code, that's an SUPG code. They were saying they were doing that 25 years ago. They were doing 40,000 calculations a year with that code. So the same technology can be used for all sorts of different problems. this is an incompressible flow solver that HeartFlow uses. HeartFlow is a company that does diagnosis of coronary artery disease. And you can see this flow solution was computed with a stabilized code that I developed in the 1990s in collaboration with the founders of this company. And the interesting thing here is they use deep learning to build the models from the images, from CTs. But they cannot get the accuracy with deep learning for the solution, and they still solve the Navier-Stokes equations. So it's a nice confluence of computational mechanics and machine learning. One area that the finite element method in its general forms really owns is fluid structure interaction, because it's so relatively easy to combine the technologies of finite elements in fluid and finite elements for structures into one formulation. So this is calculations. This is a simplified fluid structure model, although it's solving the full Navier-Stokes equations. And it was developed by Alberto Figueroa. He was a graduate student at Stanford, and I taught a course on how to take an incompressible flow code and make it a fluid structure code with sort of minimal modifications. So that became his PhD thesis. So this looks like something, obviously, the arteries, patient-specific model. And what you would think, well, maybe you could use one-dimensional elements to do that. Well, you could, of course, but this is completely done in 3 dimensions. All the discretization is in 3 dimensions. This is 100 vessels. And the properties of the arteries, the material properties, are varying, as they do in the vascular system. And the smaller vessels have stiffer properties than the larger vessels, like the abdominal aorta here is the softest, you might say. So this just gives you an idea of the level of discretization. And the fluid mesh inside is done with tetrahedra, okay? And it uses boundary layer modeling, so you get a very, very fine mesh in the boundary layers. And the shell that's surrounding it is actually triangular prisms, okay? So it's just like a triangle extruded through the thickness of the shell. And then you can do 3D studies like this. And what's nice with something like this, you can also study doing inclinations and seeing how blood pressure changes when you incline, and study the baroreceptors that adjust blood pressure when you get up very quickly and things like that. So that's an area that is owned by finite elements. Now, the variational multiscale method, I also picked 4 papers that I think are noteworthy. These are the first 2 papers that introduced it. I think probably this one is the best one for that. It introduces it more conceptually than mathematically. And then the application to incompressible flows, which I'll talk about in a moment, is contained in this paper. And from a mathematical point of view, if you want to understand the variational multiscale method, this paper is the best. Okay, this one down here. So, okay, so simple application, Navier-Stokes equations. Now, what's interesting about the Navier-Stokes equation is there's one explicit nonlinearity, and it's just the convective acceleration term here. Everything else is linear. So we're going to pose it in a space-time domain. That's 0 to t, or it could be a step, but we'll pose it from a modeling point of view for all of space-time. We're not going to compute in all of space-time, but that's how we'll think about this. Okay, so we're going to write the equation system variationally as the sum of a linear, or a bilinear form, I should say, and a trilinear form. And the bilinear form contains everything that's linear in the Navier-Stokes equations and the incompressibility condition. And the trilinear form is the integrated by parts form of the convective acceleration, this term here. So all the nonlinearity is living right here. And at the very end, you will see how the variational multiscale method sort of extracts information in different ways from the linear and the nonlinear part. So what is the method? Well, the way to think of it is we are going to do something different than we normally do. Like when you have a system of equations like this, a variational equation, you might think, well, I'm going to throw the Galerkin method at right off the bat. Okay. So what you're doing is you are representing the problem with the exact variational equation, but in a finite dimensional space. Okay. Now what you're going to view here is we're going to represent the variational equations in the infinite dimensional space, but we're going to split the space into let's say our mesh or whatever we're using, finite elements, spectral elements, NURBS, whatever you prefer, and then the rest. So we're going to segregate into a finite dimensional space, that will be our computational space, and an infinite dimensional space, which is the rest. And the way we're going to do this direct sum decomposition is by a projector. It could be the L2 projector or H1 projector, whatever you like. And that will affect the structure of things. It will affect the outcome of what the variational multiscale method produces, the part of the solution in the coarse scale space. So the projector is, if I give you V in the infinite dimensional space, the projector gives you its representation in the finite dimensional space. Okay, so it's like least squares best fit, say. And then the orthogonal complement is the part in the fine scale space. Now that's still infinite dimensional. So that's fundamental. And if you want to read that paper that I said is the mathematical paper, you will really understand how this machinery works. Now the nice thing about this is you can split the original problem into two variational equations, one weighted by the coarse scale weighting function and one weighted by the fine scale, as you see here. And the solution, of course, is just u bar plus u prime. This is an exact statement. There's no approximation here. We're just making use of this decomposition. Okay. So what we want to do, of course, is we want to compute in that finite dimensional space. So this is the equation of the coarse scales, and this is the equation of the fine scales. So conceptually, what you would like to do is you'd like to solve the fine scale equation for u prime, and if you have that u prime, you could substitute it up here in terms of u bar, okay, the coarse scale. And you have closure. That's the closure problem. That's what everybody wants to do. Now, it turns out you can show that the fine scale solution is a function of the residual of the coarse scales. This is the weak residual of the coarse scales projected onto the fine scales. It's a function of that. It's also a function explicitly of the velocity. Of course. Now, once you have that, though, you just substitute it in there, and you have closure. Okay. Now, again, this is a residual. So this is a residual-based method. You replace u bar by the exact solution. The equation is satisfied. Now, the problem is, you can't solve exactly the fine scale equation. So this is where modeling comes in, okay? And in this context, you would call it turbulence modeling. So what do? Well, we're going to identify our coarse scale space with a finite element space, call the solution, which is the velocity pressure pair, UH, and the weighting function is WH. And what we're going to do is we're going to approximate this functional representation. So that's the only approximation. There's going to be no eddy viscosity here, just like in a stabilized method. We're not going to add a viscosity in. We're going to use the structure of that fine scale solution, which is residual proportional, to define the additional fine scale contribution to the coarse scale equation. Okay, so we'll make the following assumption. Now you can show that this assumption is valid, that if you set the residual of the coarse scales to 0, meaning the solution is exactly represented in the coarse scale space, then this additional term is 0. Okay, that's not surprising. And if it's small, then in some sense this is small. And you can express that smallness by representing the solution of the fine scales in a perturbation series where the perturbation parameter is the modulus of the fine scales. And then you get a sequence of linear problems to identify all the terms in this expansion, including the epsilon, okay? And the linear problems are defined by the same matrix. It's just the sort of the right-hand side that is changing from U1 to U2 and so on. And that turns out to be an operator that you can mathematically discern, and you can get a formula for it in terms of the Green's function of the linear operator. It's the fine-scale Green's function. It amounts to a classical Green's function with the projection of that Green's function into the coarse scale space subtracted away from it. So that's what it is. And, well, how are you going to now go further with that approximation? Well, you're going to approximate this guy. And it turns out this is where you take the inspiration from stabilized methods. The double integral of the Green's function, okay, weighted by 1 over the volume, say, of the element, that's the tau matrix, it turns out. Okay, and you can estimate that. It's fairly simple for incompressible flows. So what you wind up with is the Galerkin terms. So this would be just the Galerkin method. And then you have these multi-scale terms. And if you use this idea of tau times the residual, you'll see in each case we're going to have a prime here. And wherever prime appears, you're going to replace it by these expressions of tau times a residual. Okay. And here you see there are going to be nonlinear terms too. So how does it all shake out? Well, if you write it again in terms of the initial equations, this would be the Galerkin terms. And if you use a classical stabilization method, which you just added the residuals times tau, you get these linear terms in the fine scale. But when you do what I just said, you also get nonlinear terms. You get extra terms, another cross-stress term, and the nonlinear term. And you identify this term with Reynolds stresses, and you'd identify these terms with so-called cross stresses. And the red terms, they're absent in classical stabilized methods, but you can see explicitly how the stabilization comes in. It's an approximation of the missing scales. It's a subgrid scale model. And so you have a better idea of how to deal with nonlinear problems with the variational multiscale structure. Just a couple of quick turbulent calculations. Let me see where we're at. Oh boy, I better go fast. Okay, quick calculations. Just a turbulent channel flow with splines, smooth splines in the wall normal direction. And here we have comparisons with first and second order statistics for the flow. And you can see the solutions are corresponding to a direct numerical simulation very, very accurately. 64 is better than 32. Those are quadratic NURBs. These are cubic. So anybody that does turbulence modeling would be very proud of those results. And they're automatic. Now you use these same techniques though, and you use them on every problem, just engineering problems. But the turbulence model is sort of just part of the model. How does that reflect on the initial problem we started with? What's the difference between the classical stabilized methods for a linear model problem? Well, the weighting here is minus the adjoint operator. And when you're advection dominated, all these are the same. And when you're diffusion dominated, they're pretty much the same too. So in this context, there's not much difference. A couple of calculations from the MIT group. They have a lot of work they do with Boeing. And you can see the variational multiscale, but these are compressible flows. This is a Joukowsky airfoil, much more accurate than DG for the same number of degrees of freedom. That was a drag coefficient. This is a NACA 12 calculation, comparison with 3 finite volume codes. You see the finite volume codes are nowhere near achieving the accuracy of the VMS techniques. Tau is German Aerospace. The other two are NASA finite volume codes. Those are all finite volume codes. You can see here the quadratic elements are basically just giving you the drag coefficient on any mesh exactly, and pretty close to the same on the lift coefficient. Okay. Boltzmann equation, really quickly. So the Boltzmann equation involves a probability density function. So you have convection and you have a collision operator. And the Boltzmann equation applies to these intermediate flows between molecular dynamics and the Navier-Stokes Fourier limit. And that's expressed in terms of the Knudsen number, which in that range would be, let's say, 10 to 0. It's important for high altitude flows, rarefied gases, also in semiconductor lithography. So for very small things and very large things. And this is a kinetic Struhal number, and again, the Knudsen number. So the complication in this is the collision operator. That can be different things depending on how you describe the collisions. Now, when you solve this scalar equation, the way you get fluid mechanical quantities is by taking moments. With one, you get, these are velocity integrals. The problem with this equation is it's posed in 7-dimensional space. Physical space, time, and infinite velocity space in 3 components. It's really a complicated problem to solve numerically because of that. So the moments are actually the typical flow quantities. You hit it with v, take the moment, you get momentum. V squared, you get energy, kinetic and thermal energy. And you get higher order moments too, stress tensor, heat flux tensor. Not only that, it gives you the functional form of the constitutive coefficients. So there's a lot of information hiding in these things. The problem is to get an efficient way of solving them. So what you'd like to do is take the Boltzmann equation and somehow create hydrodynamic equations from it that generalize Navier-Stokes. And this is part of the Hilbert set of problems in some sense. So to quickly go through the ideas here, we'll consider the linearized Boltzmann equation. Okay, so we'll linearize it. Linearize the collision operator. This is linear to begin with, the convection, but this is a linearization of the collision operator. You linearize about an equilibrium, a so-called Maxwellian. That's just a Gaussian, as you see here. And then the nonlinear is just this expression in terms of this perturbation, let's say. So this is the linearized collision operator, and when you take the moments of this one, you're going to get linear quantities like density, and then you get the initial density, constant density, times the velocity. And you're linearizing about 0 velocity for these things. So this is very, very simple. It turns out that the collision invariants render the linearized collision operator 0. So anything that's represented in terms of collision invariance will be zeroed out by that. And because of the self-adjointness of this operator, you can actually let it act on anything. If this is a collision invariant, it's still 0. And what you can do then is you can generate hydrodynamic equations from this. I'll say a little bit more about that process in a moment. But you can see it'll give you potentially a stress tensor and a heat flux vector, depending on how you do it. And the important thing here is entropy production. Think of entropy production here as the stability condition, the nonlinear stability condition of the theory. In this case, it'll be linear. So you need this, and you have this for the exact equations. And you want to retain this in a model. You're not going to solve the exact equations because they're posed in this 7-dimensional space. So what you do is you do a VMS decomposition. You project into the coarse scale space and the fine scale space. This is the coarse scale. Okay, that's weighted by collision invariance. The coarse scale space is the space of collision invariance. And the fine scale space is this equation here. And basically, again, you need to solve this equation and plug that in here. This is hard because this operator is a complex operator. This is its inverse. And even though it's linear, it's complicated. And it can be an integral operator, for example. And it's implicit in the fine scales. So you want to approximate the solution and substitute it in there. And you want to do that in a way that you achieve entropy production for the model, for the coarse scale equations. And that's the rub. These two guys developed a procedure, a fixed point procedure for solving that equation 100 years ago, over 100 years ago. And it's the most famous attempt, I would say, at doing this, generating the hydrodynamic equations. So what they did is they developed a recursion relationship where they sort of set this to Fn, and then they took the F on the other side, Fn plus 1. So you can just go through it. Now this was considered a big success because 0 gives you Euler, the first term gives you the Navier-Stokes Fourier system, and then you get other equations, so-called Burnett and super Burnett equations. With time, it was found out these equations were unstable. They were given crazy solutions. They don't produce entropy. They violate the entropy production principle of the model. So what we did is we sort of put entropy production up front. We took the equation, we put everything on the right-hand side, we made this approximation of order the Knudsen number, and then we applied this operator to that residual of that equation, and then added F tilde to both sides and developed a new fixed point iteration. The first one gives you Navier-Stokes, and the second one is this. It gives you a system here, and you get these additional terms in the constitutive laws, okay, to Navier-Stokes. And I'll just show you quickly a couple of solutions, very simple solutions, essentially heat transfer between two temperatures and the generalization of Poisson flow. And what I'll point out is this model now gives you exactly what the linearized Boltzmann equations do, right up to infinite Knudsen numbers, surprisingly. This is for stationary heat transfer. This is the heat flux. And you can see other models like Navier-Stokes just go nuts, and some of the other expansions don't work very well. And for Poisson flow, this is the mass flux. You can see it's very different from the Stokes solution. And it agrees, again, with a linearized or exact effectively solution of the Boltzmann equations. So with that, I'll tie it up. I'll say that the VMS method provides a framework for new Boltzmann moment closures. This has been an outstanding problem for basically 100 years. So this is interesting from the standpoint of all the applications, as I mentioned, in the kinetic theory community. So we derived a novel entropy-stable VMS-based closure. And I should say, I have to give all the credit to my PhD student, Frimpong Bedo, and former postdoc, now professor at Eindhoven, Michael Abdul Malik, who really introduced us to the Boltzmann equations. They were the principles behind this work. So for the linearized Boltzmann equations, every term in the sequence is entropy stable. For the nonlinear, the analog of the Burnett equations is also entropy stable. That's a really surprising result, but it is entropy stable. So we have a model there, and we're working further on that. And analytical solutions got good agreement with benchmark problems. Some of the benchmark problems are very simple, as you can see in this area. Future work, boundary conditions, as always. It's even a bigger problem here, because you're trying to take boundary conditions from kinetic theory, which are not intuitive, you come from the continuum point of view, and translate those in a rational, let's say, decomposition into coarse and fine scales for the hydrodynamic equations you generate. And we need to explore the nonlinear theory, and we're doing that more, and look into perhaps other entropy-satisfying closures. And then another level of VMS and stabilized methods, build the numerical method for those equations. So that brings in another stabilization, as before. So with that, I'm done. Thank you.
Very detailed and interesting presentation. I think we have time for one or two questions. Go ahead, please.
Thank you for a very nice talk. I had a question regarding the projector you're using for the VMS approach. I'm working on pretty much the same thing, and I want to hear your opinion on how do you dictate the choice of projector for your VMS approach?
Well, that one paper that I mentioned, the mathematical paper, it studies if you're familiar with that paper, it studies the different results you get for the L2 projector and the H1 semi-norm projector. And in one dimension, with C0 finite elements, what you can show is that the n-node values with the H1 seminorm projected will always give you the exact values.
Yeah. Totally exact.
Yeah. And in between, where the function is smooth, you get the H1 seminorm best fit. Now, okay, is that great? I don't know. I wouldn't say it's great, but that's what you get. L2, unfortunately, gives you the fine-scale Green's function becomes global. Okay. Now, you're going to localize this thing no matter what, in a practical consideration. But I think the H1 is a little bit more robust, let's say. Yeah. And once you do that, you can remove terms from the variational equation because of that orthogonality property. The other thing is what you find there too, which is extremely interesting, is you can re-represent things that were written in terms of the fine-scale Green's function, which we analytically computed in that paper, by a constant tau, but higher derivatives of the residual. And when you do that, it wipes out the diffusion operator. So it looks like an artificial diffusion method, but it's really a weighted residual method. So there are some interesting directions to pursue there in different contexts. One of the things we're looking at right now, and we haven't made a lot of progress yet, but we're looking at advective, diffusive, reactive, dispersive systems, like 5 equation systems, but with all of those operators. And the dispersion operators are at least third order. So that really requires some competing requirements of your method. So we're trying to work that out. But that's kind of the action area right now. And that's for different applications that you might consider. Yeah, cavitation is one of them. Yeah. So I can't help you because I don't know what your problem is.
Hi, I was very nice talk. Interested in where you're going with the Boltzmann equation. Have you managed to do flow past the sphere? Because there's a free molecular solution.
Yeah, no, we haven't. What you've seen is basically what we've. There's a little more now. We did some things where we calculated various moments of solutions and all, but no, we're really. I'd say, especially me, I'm a neophyte. We're just getting started. Yeah. But we feel we have maybe a new machine to come throw into the mix.
So let's thank Professor Tom Hughes again.
Thank you.
Very interesting.